All right, we continue doing hypothesis testing. This is called difference of proportions. Now this will correspond to assignments 27 and 28, a double assignment, therefore 24 points, pretty significant. Your homework will be comprised of 3 questions, so they'll all be worth 8 points. So take your time, be meticulous with these, multiple parts, 8 points per question on your homework, keep that in mind. Difference of proportions. All right, we're comparing 2 populations now. And we're going to see if there's a significant difference between the percentages related to these 2 populations. So, if you would look at example number 1 here, we have some data about traffic fatalities related to people who are wearing a seatbelt and people who are not wearing a seatbelt. All right? So, we have 2 populations. I think it makes sense to label them first. So population number 1, I suppose, would be the people who wear a seatbelt, all right? So any reference to 1 throughout the question, just keep in mind, would be in reference to the population of people, the data from people who wear seatbelts. And population number 2 would be people who do not wear a seatbelt. Not wear seatbelt. It doesn't really matter which one you call 1 and 2. I usually would just suggest you put them in the order that you see them in the question. So we have 2 groups of people, and so let's continue on. So the question, now remember, 1 would be people wearing seatbelts, 2 would be people not wearing seatbelts. So here's the key question here. And I would also tell you that the steps for setting up the hypothesis test are the same as they've always been. The null would be equal, the alternative would be less, greater, not equal. Then we talk about, all these steps, test statistic, lower upper tail, two-tailed, all that. This is a copy-paste of the previous 2 assignments as to the traditional method for performing a hypothesis test, which is the method that I prefer. All right, so keep that in the back of your mind. And so when we're reading this question, here's the deal. Right here it says, is the fatality rate for those who wear a seatbelt, population number 1, is that lower than the fatality rate for those who do not wear a seatbelt? So a fatality rate would be a percentage, the percentage of people who wear a seatbelt and are involved in a fatal accident. So that lower would be related to our alternative hypothesis. Now what I like to do here is underneath here, I would say, is the fatality rate for people who wear a seatbelt would be considered P1, the percentage of people who wore a seatbelt and unfortunately resulted in fatality. Is that fatality rate lower than what it would be for the other population, people who do not wear a seatbelt? So is the fatality rate for people who wear a seatbelt, P1, lower than P2? Now, I put that underneath the alternative because we're going to do a very quick algebra manipulation to this to change it into a difference in proportions, as it mentions. So what we'll do is we'll set that up, and then we'll subtract over the P2, just a little algebra here, and if you transfer this up here, we would have P1 minus P2 is less than, 0, wouldn't it? So that's why it's called a difference of proportions. See, basically, if you take the first fatality rate and subtract the second one, and it's less than 0, that also means that the first fatality rate was lower than the second fatality rate. So I always write this underneath here and then transfer it up there and make it into a difference of proportions. All right, so is that difference less than 0? Which is the same thing as, is the first fatality rate lower than the second one? These are interchangeable algebraic expressions, all right? So, there's that. That would be considered, and again, the key word being lower, as it was expressed at the end of the question. Well, so the corresponding null hypothesis would be that that difference is equal to 0. Let's talk about it. If you take one percentage and subtract another and you get 0 for an answer, doesn't that mean that those percentages were essentially equal to each other? In fact, they were equal. A lot of people will even say, it doesn't make a difference if you wear a seatbelt, right? There's no difference. There's no difference between the two fatality rates. That's what that says. So we assume that there's no difference between the two fatality rates. As always, we give the null hypothesis the benefit of the doubt, and then we see if there's enough evidence to reject that in favor of this. And I would again point out that the alternative in this case is that wearing a seatbelt will lower your risk of fatality. So lower fatality rate, less than. So if you wear a seatbelt, if you're part of population 1, if you wear a seatbelt, your chances of dying in a wreck are lower than if you don't. That's what that is saying, the alternative. Okay, so we assume that the null hypothesis is true, that it makes no difference. All right, now on these, the test statistic, yeah, it's a flow chart, but I'll tell you what, it's going to be the same on every one. So you'll notice I've already written that up here in the interest of time. I'm going to leave it up here for all of these examples. I will flat out tell you that on assignment 27, 28, the 3 questions you're going to do, that test statistic will be the same. And we'll dig into the details of it when we get to the compute part of the process. All right, so write it up there and don't worry about it yet. We'll get to it later. It's beautiful. You're going to love it. Okay. But the thing to keep in mind here would be that it says Z equals, so that impacts our rejection region as it has before. So we're back to good old friend bell curve, 0 in the middle, and all that discussion about lower, upper, and all that. Okay, well this will be a lower because of less than, as we've seen on the previous 2 assignments. And the value of alpha in general is arbitrary, but this person says let's use 1%. So if alpha is going to be 1%, I'm hoping that this makes more and more sense each time you do these. We're going to give 1% of the bell curve to the alternative hypothesis, and since it involves less than, lower fatality rate being the key word, that'll go on the lower tail, won't it? So we're putting 1% in the lower tail, and we're going to give the entire rest of the bell curve to the hypothesis that it makes no difference whether you wear a seatbelt. See, so we're giving that the benefit of the doubt, and we're seeing if the data proves otherwise. Again, it's always in reference to, I'll give you the benefit of the doubt, null hypothesis, but I'm going to see if the data is such that I can reject that assumption in favor of this. That's how it always works. It's like a court case, innocent until proven otherwise. All right, so, hey table wants middle sliver. If the lower tail's 1%, the middle sliver needs to be 49%, right? This table always wants that middle sliver. There's other tables out there. This is the one I'm giving you. I don't want to give you 10 different tables and you got to figure out what table to use. When I used to do that, it was disaster. It seems to have gone way better once I said, let's just learn one table and stick to it. So 49% middle sliver is going to be 4901 is what I see there. And so that's 2.33. And note that because of the less than, that would be negative, right? Okay, so is the fatality rate, if you wear a seatbelt, lower? That's what drove the whole discussion, lower, less than. All right, so won't we reject the null hypothesis if our z-score turns out to be less than that negative 2.33? And a lot of people would say that these parts that we filled in so far would be like a judge giving the jury their instructions before we go perform the trial. When you go perform the trial, that's when you go collect data and stick it into your test statistic in the analogy of the court case. So this is where obviously the numbers in the question come into play. I hope you remember that when we have p hat, when we put hats over these p's, we're talking about percentages that come from samples, right? So this is where the data in the table would come into play for these various p hats. So let's identify those values. Let's start right here. P hat 1, wouldn't that be the fatality rate in our sample of people who wore seatbelts? I'll remind you, 1 is the wearing seatbelt group of people. So in 250 accidents involved where people wore a seatbelt, 10 of them resulted in a fatality. That's 10 divided by 250. I can't guarantee you that these will divide out nicely every time. I believe on some of the questions I made them divide out very nicely. That is a 4% fatality rate. We'll talk later. I'm pretty sure I have an example later where it doesn't divide nicely, and if it doesn't, we'll leave it in fraction form. Okay, but I conjured up the numbers here to make them work nicely. P hat 2, that would be the sample data from people who did not wear seat belts. In 500 observed accidents where people were not wearing seat belts, 65 fatalities, 65 out of 500. 65 divided by 500. Come on, man, be a nice decimal. Yes, it's 0.13. Now look, doesn't 4% look lower than 13%? Of course it does. It looks lower. But a statistician doesn't just say, well, yeah, that's lower, case closed. That's sample data. You can't just make the leap to population just based on one sample. But it is pretty compelling that that fatality rate looks lower than that one for those two samples. All right. The other component of this, and I can already tell I'm about to run out of room, so I'm already getting nervous here, but we'll make it work. Okay, P bar back here, that's the other thing in this beautiful formula. P bar is what they call the pooled percentage. In other words, what would be the fatality rate for the two groups if you combined them? So what we do is we take the total number of fatalities and divide it by the total number of accidents, and that would give us our pooled percentage here. So the idea would be, see, this is X1, N1, this is X2, N2. So if we add the fatalities, 10 plus 65, and add up the accidents, 250 plus 500, not really adding the two fractions, you're combining them into one fraction, is what's happening mathematically. So I hope you get the understanding of what that is. Total fatalities divided by total accidents. What was the fatality rate for all people regardless of seatbelt usage? And so that would be 75 total fatalities out of 750 total accidents, 10%. So P bar turns out to be 10%. And Q bar, therefore, would be 1 minus that, which is 90%. All right, so somebody made the numbers up so that the math would be easy for us. And all those numbers go in here, all right? And you can tell I'm out of space. I usually would do continue the computation clear over here where you can't see me. So I'm gonna have to go with the flow here. So I hope you guys can remember what these numbers are. I hope I can remember what they are. I'm gonna plug them in this. All right, that's 4%, that's 13%, that's 10%, 90%, N1, sample size number 1, and so on. All right, so hit pause, write them down. I got to erase to make room. That's 4%, that's 13%. Whew, I was nervous I was going to forget those. All right, that was the percentage from our sample data of people that wore seat belts. That's the percentage in our sample data. People did not. All right, now minus. Now, here's the interesting thing on this. You're like, you don't have much room to put that there. Fortunately, I don't need much room because I want to remind you, we're assuming that the difference in the population percentages is 0. And I'm just going to tell you that the questions I'm giving you on this, that'll be the case. That assumed difference between the two populations will be 0. All right, so we're basically saying, all right, there's no difference between the two populations. So that'll be 0 every time for the questions we're going to do. There's other situations in life where it might not be, but I'll just tell you flat out right now that it'll work for us. All right, then the pooled percentage, the pooled fatality rate was 10%, I'll remind you. And then therefore the Q is 90%, 0.90. Sample size number 1, that was the 250 fatalities, or 250 accidents involving seatbelt. And then again, P bar 10%, Q bar 90%, over sample size number 2. That was the 500 accidents involving people not wearing seat belts. Okay? So again, I apologize for having to scroll things back, but I hope, hit pause, write things down. There's our 10 and 90. Okay, you know what the snob is going to say now. That's calculator buttons. And the answers are on the next slide as to what that z-score comes out to be. And all I can tell you is this is order of operations, which the snob, I hope you understand. I mean, Mr. Snobgrin can't, I'm not here to help you poke buttons and do this. This is order of operations. I would suggest you figure out that fraction, and if you're not sure what else to do, write it down, figure out that fraction and write it down, and then add them, and then take the square root, get your denominator, break it into smaller pieces. This is all order of operations, all right? And that comes out to be negative 3.873. Negative 3.873. And if you can't see that on the board, look at the next slide. It was uploaded to you, all right, negative 3.873. And you would hopefully look at this picture and you'd say, that's out there below the negative 2.33. It is in that lower rejection region. It is less than this number. If you want words, look at this. If you want pictures, look at this. Double arrow, interchangeable. That would hopefully lead you to say, yeah, we should reject that null hypothesis. Look, we gave the majority of the bell curve to the assumption there's no difference between the two fatality rates, but the data proved otherwise. We're going to reject that null hypothesis, which favors the alternative. And so, again, looking back at the question basically said, is the fatality rate for people who wear seatbelts lower than people who do not wear seatbelts? And I think this data would indeed support that. So, again, as I keep saying, we're using the wording of the question to formulate the answer. And so, wouldn't it be fair to say, using 1% significance, good statisticians always report that, because as we've seen before, different levels of alpha could produce different outcomes. But it does indeed seem that the fatality rate for people who wear seatbelts is lower than the fatality rate for those who do not. So, there you go. That's one example of that. I think we're going to do maybe a couple more and then hope for the best. So, I know there's a lot going on right there, but if you just take your time and walk through each step and be very careful, I think you'll be just fine. Easy for me to say, I miss you guys.